Hey, how's it going, John? Just let me know if you guys have any questions or anything. Number 14. Let me double check what that is. Here, it's on my other laptop. 1 second. Number 4. Okay, number 4. Yeah, we could. You're talking about the one where you have to do Lewis structures and then figure out sections. You're talking about the one with the Lewis structures. It was like 4 molecules, and you do the Lewis structures to figure out the intermolecular forces, right? Because that one I know. Okay. Let me double check. Here, 1 second. The mole house. Number 4. Oh, okay. I was looking at the wrong spot. The one says if 42.1 liters of oxygen gas react with nitrogen gas to produce nitrogen dioxide gas, what volume of nitrogen dioxide is produced? About the balanced equation using the mole house. Okay, yeah. So this is probably the shortest possible stoichiometry question you'd get with gases. This is the shortest kind you would possibly get. Because the other kinds of questions you'd see are just like straight up basic stoichiometry problems, really. But this one is a little bit more unique. So let me show you. So basically, I'll do the mole house first. And just give me a minute. Okay, so we got grams, liters, moles, 22.4, 22.4. Okay, so our given was oxygen gas, and we're trying to go to nitrogen dioxide. Okay, so our given was liters of oxygen gas, and I'm trying to get volume of nitrogen dioxide, so I'm trying to get liters of nitrogen dioxide. All right, so this is basically like my path right here. Right, so my given is liters of oxygen gas, 42.1 liters of oxygen gas. So I'm trying to get volume of nitrogen dioxide, so I want to get liters of nitrogen dioxide. So I'm going from liters to liter the other side. All right, so the reason why this one's so quick, I'll show you the long way. If we just treat this as a normal stoichiometry problem, like before we got to any of this stuff, when we're just doing stoichiometry still, you'll see that a lot of stuff can cancel, right? So you get 42.1 liters of oxygen, and first you're going from liters to moles, then you're going from moles to moles, and then you're going from moles to liters, right? So there's just like the bare bones of it, right? So there's 3 doorways, so 3 fractions. So you're going from liters to moles, and then from moles to moles, that mole ratio, then from moles to liters, right? But we have to write the balanced equation first. Let me do that on the other side, so I don't have a lot of room. So oxygen and nitrogen. I'm going to leave off the phases of matter just to make it quicker. That's my laundry machine, by the way. So yeah, this is the balanced equation, right? So 2O2 plus 1N2 goes to 2NO2, right? That should be balanced. And so we know it's going to be 1 there and 1 there for moles, right? 1 for moles up there because it's moles by itself, 1 for moles down there because it's moles by itself on that fraction. This is the mole ratio, right? So for the mole ratio, we're exiting moles of oxygen. So then the coefficient is 2. And sorry, it's not nitrogen, it's nitrogen dioxide. Here, I still have a lot of space. Let me see if I can make this a little bit clearer. 1 second. All right, so there's the mole ratio. Right, so we're going from oxygen to nitrogen dioxide. I misspoke earlier. Nitrogen dioxide's up there. So they both have the coefficient 2. Right, it's 2 for oxygen, 2 for nitrogen dioxide. So it's going to be 2 over 2 there. And then liters is always 22.4. All right, so liters is always 22.4. So I have 22.4 down there, 22.4 up there. But you'll notice doing it like this is doing it like a normal stoichiometry problem. Right, so it's like a typical stoichiometry problem. We're going from liters to moles first, that's that part. Then we're going from moles to moles, right, so that's the coefficients here. And then we're going from moles to liters. That's why we have 1 on the bottom, 22.4 on the top. But you'll notice if you're going to go from liters of one gas to liters of another gas, so specifically from liters to liters, right, if you're given as liters, and if you're trying to get liters from the other substance, which is always going to be this path, this little like upside down U, these first and last fractions are going to always cancel. It's kind of pointless having them here. It's 22.4 on the bottom, 22.4 on the top. So those are going to cancel right away anyways, something like that. So it's not always going to be like this. But because the first fraction and the last fraction are always going to cancel if you're going from liters to liters, we can instead just do it like this. Let me just show you the other way. So instead of using a mole ratio, it's the same thing, but we call it a volume ratio. So you're just going to use the coefficients, right? So let me just say that all again in case it's kind of confusing, right? So I did it like this, like a normal stoichiometry problem, 3 fractions because I'm going through 3 doorways. Going from liters to moles, so 1 for mole, 22.4 for liters, then moles to moles, so that I have the coefficients here, and then from moles to liters, which is this last little doorway, right? So you're always, if you're going to go from liters to liters, specifically from that unit to that unit, it won't work for grams to something else, but if you're going from liters to liters, the first and last fraction is going to cancel because it's 1 over 1 and 22.4 over 22.4, so they're always going to cancel. So the only fraction that makes a difference really is this one, the mole ratio, but instead we just call it the volume ratio, but it works the same way. These are just the coefficients, right? Ironically, in this case, it doesn't make a difference either because it's 2 over 2. So the answer here is just 42.1. So the answer is the same as the given in this case. It's not always going to be that way, obviously. If it was a different coefficient, if it was maybe like 2 over 1 or 3 over 2 or something, it would make a difference. In this case, it's just going to be the same number as the given then. So again, if you're going from liters to liters, let me fix that L. If you're going from liters to liters, it has to be from that unit to that unit, from liters to liters. This won't work for grams to grams or anything like that. You don't need to worry about that fraction or that fraction. Right? Technically, it'd be the same if you're going from particles to particles, because you'd have Avogadro on the top and bottom. They would cancel. So you're not going to see that anyways. So yeah, the only fraction that makes a difference here if you're going from liters to liters is the mole ratio. So we just put that down, make it shorter, and we call it the volume ratio. But it's the same, use the coefficients. In this case, yeah, you're right, it's just 42.1. So this answer is kind of like a silly trick question, I guess. Not really a trick question, but it's just kind of like silly because the answer is the same as the given. So yeah, you're right, it's 42.1. And since it was the same number as the original number, it made me think, oh no, yeah, you're fine. You did it correctly. You're good. So yeah, this one is just a weird case. If it was asking for something else, if it was asking for nitrogen instead, then, you know, it would have made a difference. If it was asking for nitrogen, right? This isn't the problem, but if it was asking for nitrogen, it'd be 1/2. And in that case, you'd get a different answer, but yeah. So if you're going from liters of gas to liters of another gas, just use the mole ratio, but instead of moles, just make it liters. So we call it the volume ratio. All right. Hopefully that made sense, but let me know if you have any other questions at all. Hey, Mohammed. Yeah, no problem. Yeah, so that's just the volume ratio, and it only works for going from liters to liters. Technically, if you're going from particles to particles, it'd be the same idea, just using the middle fraction, but I mean, that's not going to show up anyways. And, you know, when in doubt, you could just do it the traditional long stoichiometry way and you'd still get the right answer, so. Yeah, let me know if you guys have any other questions about the study guide. Most of the answers are up on it, but there are some like that one I didn't put the answer for. But yeah, most of the answers should be up. Number 4, is that the first section? So all the intermolecular forces and stuff? The one with the intermolecular forces? Yeah, okay. So those solutions are on line 2. They're just on like the last page. I didn't have enough room, but I can go through them with you. I might just go through the Lewis structure steps kind of quick, unless if you would like to, I can go through the Lewis structure step like step by step too. Yeah, I'll do the first one kind of step by step. So for the first one, it's CH4 methane, right? So again, we're just going to do the Lewis structure first for CH4. So carbon has 4 valence electrons. Hydrogen has 1, but there's 4 hydrogens, so it's 4 times 1. So we have 8 valence electrons total. Carbon's in the middle. The hydrogens are surrounding it. All right, so those are just the first 2 steps. It's got the valence electrons and put the bare bones of this thing like situated. I don't put the bonds on it yet. We know it's gonna have 4 single bonds because of the hydrogens, but let's just do it step by step. So for this third step, we take what they want minus what they have. Carbon wants 8, but hydrogen wants 2. So I'm gonna do 4 times 2 because there's 4 of them. And then I'm gonna subtract the valence electrons from the first step, divide it all by 2. So we just get 8/2, which is 4 bonds. All right, so I'm gonna put the bonds down. All right, so we're pretty much done with the Lewis structure. I'll do the last step, even though we know the total valence electrons, which is 8, minus the number of electrons used in bonds, which is 8. So we're gonna have 0 dots, right? So then we hopefully expected that because hydrogen is only ever gonna have 2 electrons. It's only ever gonna have 1 single bond on it. Hydrogen will never have 2 bonds. It will never have dots or anything. Hydrogen is only ever just gonna have a line next to it, just a single line, right? And carbon wants 8 electrons, and it has 8, right? It has 2, 4, 6, 8, because each of those counts as 2. So the Lewis structure is done here, right? So then for the Vesper shape, the next step, the 5th step, we're looking at the Vesper shape here. You're looking at the central atom. The central atom here is carbon, and it's surrounded by 4 single bonds. So in the central atom is surrounded by 4 single bonds, like this. It's tetrahedral. Right, so this is a tetrahedral shape. I'll see if I can like kind of draw it. It's probably the hardest one to draw on a surface because it's very like 3-dimensional. Right, so tetrahedral, it's supposed to be kind of like a tripod-y looking shape, right? So kind of like that. Let me see if that makes it better, hopefully. So yeah, it's tetrahedral. And then we want to next see the polarity, right? So the polarity is the next step. So in this case, with tetrahedral, there's symmetry. No matter which way you rotate it, it's always going to have carbon in the middle and have all the hydrogens evenly spaced. I think it's like 104.5 degrees. I might be mistaken. But it's a little bit more than 90. I think it's 104.5. So it's the same angle between each of those hydrogens between each of the single bonds around the carbon. So there's symmetry here. And so because of the symmetry, we know that everything around it should be evenly placed. All the electrons in the bond should be evenly placed, especially if it's surrounded by the same atom. And it is. So carbon's surrounded by a hydrogen, hydrogen, hydrogen. They're all hydrogens, right? So because it's all the same atom that surrounds carbon, and there's no lone pairs here, no lone pairs there, no lone pairs there, no lone pairs there. It's just hydrogen. So really the only electrons here are the single bonds. And no matter which way you rotate it, the single bonds are always going to have that angle 104.5 in between them. So they're always going to be evenly spaced. So because of the symmetry here, we know it's nonpolar, right? So it's nonpolar. So nonpolar for that step. I'm using letters, so now I'm on letter G. So I guess the 7th step. So for the intermolecular force here, because it's nonpolar, it has to be dispersion, also known as London dispersion. So it's going to look like it's going to be dispersion for your final answer, basically. Right. So keep in mind, though, this is nonpolar because it's the same exact atom that surrounds carbon. If one of these was like a chlorine, like if this guy over here that my finger's on top of, if that was a chlorine or a fluorine or an oxygen, any other element, then there would have been polarity. Because if one of these was a different element, if this one right here was something else, there probably would have been some lone pairs on here. Like if it was an oxygen, there probably would have been at least 2 lone pairs. There'd be probably 3 lone pairs in that case. So it would be more negative over here. So then it would be polar bonds here, and they're all evenly spread out from each other. So it's nonpolar, right? So I'll do the other ones, but I might go through the Lewis structure steps a little bit quicker. Just 1 second. Yeah, like this next one, for example, is what I was just talking about, actually. So for CH3Cl, the next one here, I'll just go through the Lewis structure pretty quick. So it looks like this. Right, so that's just the Lewis structure without thinking about the Vesper geometry yet. Let me know if you have any questions about that. The quickest way to do Lewis structures too is also just think about the valence electrons. So carbon has 4, hydrogen has 1, so there's 3 hydrogens, so that's 4 plus 3, that's 7. And chlorine's got 7, so that's 14. So we have 2, 4, 6, 8 from the bonds, 10, 12, 14 from the lone pairs. So this is the Lewis structure. And so now we gotta think about the Vesper shape. So again, I just did the Lewis structure quickly, so let me know if you have any questions about that. But for the Vesper shape, kind of like before, it's an atom in the middle with 4 single bonds around it. So since it has 4 single bonds around it, it's going to be tetrahedral again. But in this case, it's what I was actually hinting at before. It's not surrounded by the same element. Right, so even by nature, tetrahedral structures are symmetrical. And what I mean, carbon is not surrounded by the same element. There's 3 hydrogens here, and this one's a chlorine. And this chlorine has 3 lone pairs. That's 6 electrons on the outside of it. So this one right here is this part, wherever the chlorine's at, if it's on the top or the left or wherever you rotate it, it's gonna be more negative by that chlorine. Ooh. I hope that washes off my pants. So it's going to be more negative where the chlorine is, more positive wherever the chlorine's not. So this one is polar, right? This one's polar. And then the intermolecular force it has, well, if it's polar, it's either going to be dipole-dipole or hydrogen bonding. And then remember, hydrogen bonding, the hydrogen has to be bonded to an N or an O or an F. And none of those are even here. The hydrogens are just bonded to carbon. So this is going to have to be dipole-dipole. So this one's dipole-dipole. All right, so let me know if you have any questions about this one. How do you know whether C goes in the middle or chlorine? Oh, good question. So basically, it's something, it's been a long time, but back when we did Lewis structures, like last semester, I think it was, when we looked at Lewis structures, carbon pretty much is always the most central. It's always, if you have a carbon, it's always in the middle. And carbon pretty much, I don't know if you've ever noticed the trends, but kind of like how hydrogen only ever just has one bond. Carbon typically just has bonds around it. So it might just be 4 single bonds, or with CO2, for example, with CO2, carbon might have 2 double bonds. Carbon just always has bonds. It never really has lone pairs like ever. Yeah, it's a rare thing. So carbon always has the bonds. It's always the most central atom. Yeah. That's something I don't know, because I know it's been a while since we did the chemical bonding unit, but I don't remember if I told you guys or not, but on the second step, like the second step here, when you're just putting down the bare bones, not with the bonds yet, not with the lone pairs, but if you're just putting the bare bones down and you want me to double check like which one is in the middle, which one goes where, I don't mind pointing you in the right direction for that. So if you accidentally put chlorine in the middle on that step, I would have been like, hey, the chlorine goes on the outside, put the carbon in the middle. I won't say anything else, but I mean, in this case, I guess that doesn't apply because it's online, but yeah. Yeah, let me know if you have any other questions about this one. So viscosity is basically, it relates to the intermolecular forces that are within that liquid, causing it to have more friction. So if something has stronger intermolecular forces like hydrogen bonding, it typically moves slower. So viscosity is basically, I don't want to butcher the definition, but it's basically, if something's more viscous, it's going to be thicker, like molasses or honey, and it's going to move slower. I just want to make sure I don't like butcher the definition of viscosity. Where are we? Yeah, so it's because of the internal friction, because of the intermolecular forces. So if something has dispersion forces, which is the weakest, it's not going to be that viscous. Like for example, water has hydrogen bonds, and so because of the hydrogen bonds, it's more viscous. So it's kind of like, I don't remember if I showed you guys that video. I don't think I did it as a demo, but I showed you guys droplets on the penny because it had a stronger bunch of intermolecular forces. It was hydrogen bonding, and so there's much more internal friction within like a puddle of water, for example, than like a puddle of rubbing alcohol, because rubbing alcohol would be a dispersion forces. It's weaker intermolecular forces. So yeah, viscosity is basically the internal friction of the liquid causing it to move slower. It's basically, so if something's more viscous, it's going to be moving more slowly. It's going to be a thicker liquid. So it's going to be a little bit more like sticky and slowly moving. I'll be right back. One. Yeah, let me know if you have any other questions at all. Yeah, so basically vapor pressure, because again, at the surface of liquids, at the surface of any liquid, there's a little bit of evaporation going on. So some of like the liquid particles on the surface are going into the gas state, but they're also in equilibrium between liquid and gas. So they become a gas and they end up condensing with maybe some of the other gas particles and they become a liquid again. And then because they're on the surface where, more heat's going to get absorbed, that's the immediate spot where they're going to feel any sort of heat from their surroundings. Because, if you have like a cup of water, for example, it's an open system. So here, one second, let me erase this stuff. All right, so I guess I should be careful with my words because we haven't really talked about open systems and surroundings yet. That's the next unit. But if I have a cup of water, I'm just going to make the little circles water molecules. I'm not going to draw the whole H2O thing right now. But the main place that they're going to feel any sort of, heat from their surroundings, which is everything outside of them, is going to be the surface of the cup, right? Because everything else is enclosed within. So the surface is where vapor pressure happens, which means it's the pressure due to the particles that evaporate and become a vapor. So some of them, they evaporate and become a vapor or a gas, right? And they're in equilibrium, right? So that means that they're kind of constantly going back and forth both ways. So some of them become a vapor, and then they condense back down to a liquid, and then they get more heat and become a vapor again, but then they condense down with the other ones that they meet up with and become a liquid. So they're kind of going back and forth. So if something has high vapor pressure, that means that they're less viscous. They have weaker intermolecular forces, right? So if you think about, like, for example, something like water versus like alcohol, you can smell the alcohol pretty easily because it uses dispersion forces. So alcohol uses dispersion forces. So when alcohol is in here, like, just imagine this is alcohol instead of water now. The intermolecular forces between all the alcohol molecules, they're weaker. They're not holding each other that tightly, so it's easier for them to evaporate and become a vapor. So vapor pressure is just the pressure on the liquid due to the evaporated particles of itself, if that makes sense. Because at the surface of any liquid, even something with strong intermolecular forces like water, which has hydrogen bonding, even water, they're going to evaporate, right? So it's kind of like, it's a boring demo. I've done it before, but it's not super exciting. But, if you kind of like have an Erlenmeyer flask, and like seal the top of it and just leave some water in there by a window near the sun, you'll see that, you're going to get some like little dewdrops, some little like condensed water vapor molecules on the sides of the empty part of the glass container. And again, it's because they're evaporating at the surface. So vapor or evaporation happens at the surface of the liquid. Vapor pressure is just the pressure on the liquid due to those evaporated particles. So something with high vapor pressure is something that has weaker intermolecular forces, like alcohol. And so a lot of the things that you can smell easier, like perfume, alcohol, oils, they use dispersion forces. They're non-polar molecules. So they have very weak intermolecular forces here holding them together. So because they have weaker intermolecular forces, they evaporate easier and you can smell them easier. So we call those more volatile. Those are volatile substances. So like perfumes and stuff, or gasoline, those would be volatile. Yeah, let me know if you have any other questions about that. I'm just gonna go back to the other ones Ryan was asking about. Oh yeah, no problem. So yeah, so any substance will evaporate at the surface, even things like water, if strong intermolecular forces. But if the intermolecular force is weaker, like dispersion force, which happens with nonpolar molecules like alcohols, gasoline, things like that, it's going to be easier to smell them because they're evaporating a lot more. They have higher vapor pressure. All right, so for CO2, it looks like this. Again, I'm just going to put the Lewis structure down real quick. So this is back at the one Ryan was asking about, number 4. This is the third part of number 4. So CO2 looks like that. So with CO2, the central atom is carbon, and it just has 2 double bonds. So this is going to be linear. So this is a linear structure. It's kind of weird drawing it again. It looks the exact same. Yeah. So it's a linear molecule. And so now to look at the polarity, carbon is surrounded by oxygen and oxygen. It's the same exact element. And it has the same number of lone pairs here and the same number of lone pairs over there. So 2 lone pairs, a double bond, another double bond. So there's symmetry here. So this one would be nonpolar. And so the only intermolecular force for nonpolar molecules is dispersion. So it's going to be a dispersion force for CO2. So that's the third one, 8. So the C's are going to be in the middle, and hopefully you guys would remember hydrogens never go in the middle because hydrogens have to have just a single bond on them. All right, so this is propane, the C3H8 from number 4. This is the last one from number 4, letter D. So this is the Lewis structure. So when it comes to the Vesper shape of this thing, it's kind of tricky because the central molecule is carbon, but it's also surrounded by this carbon, that carbon. But really, you can just look at this one being the central molecule. But you know, it has 4 single bonds around it, and this one has 4 single bonds around it too, and so does that one. So it's a little bit tricky. It's kind of like linear, but also tetrahedral. This was kind of a tricky one to put on the study guide. I wouldn't put this one on the test. So it's linear, but it's also tetrahedral. Let me see if I can draw it out. Yeah, it's also on the study guide too. So it's going to have H there, H there. This one just has 2 H's. This one's going to have H there, H there. Kind of hard to draw this one. But yeah, it looks a little bit like that. All right, so it's sort of linear, but there's also some tetrahedral structures here. I probably messed up making these ones too close together. These ones should be a little more spread out, the H's. But you can tell there's still symmetry, right? Because there's just carbon here, carbon there, and they're just surrounded by hydrogens all over. So again, with polarity and non-polarity, you want to see if it's asymmetrical in terms of the distribution of charge. If there's an asymmetrical distribution of charge, it's going to be polar. Bonds here, single bonds there. All the carbons are surrounded by 4 single bonds, and they're all surrounded by the same exact element, just hydrogens, right? Just all 8 of these hydrogens. So this is a non-polar molecule, right? So it's a non-polar molecule. So for this one, it would also be dispersion. Yes, this one would also be dispersion. But yeah, if you did want to do it that quicker way, like an OChem, it would just look like that, or like that or that. But I mean, we probably won't get there. We have 3 carbons. Each corner is a carbon. But anyways, so yeah, that one's dispersion as well. Yeah, let me know if you guys have any other questions at all, though. The drawings, I put the answer and the drawings to that on the study guide on Canvas, so it might look nicer on Canvas than on here. It might look a little bit more easy to read. But yeah, let me know if you guys have any questions. No, I wasn't sure what to put. What type of substance? High vapor pressure. Oh yeah, so for high vapor pressure, number 7, what is vapor pressure? So yeah, vapor pressure, like I was telling Muhammad, is just the pressure due to the evaporated particles on top of the surface of the liquid they evaporated from. Solids do have vapor pressure. We especially see that being the case with specific solids that undergo sublimation, like carbon dioxide, which is dry ice. What types of substances have high vapor pressure? So things that have high vapor pressure would be substances that have very weak intermolecular forces. So substances that have dispersion forces, you can put that down as an answer. It's totally valid. So for that part, you can say nonpolar molecules that have dispersion forces, they're going to have high vapor pressure because like they're not being held together as tightly. So it's easier for them to evaporate and exert pressure on top of their liquid. So yeah, let me see what the exact one is. You wouldn't see something like that on the test. But propane, some of them, it's like almost a hybrid of more than one Vesper shape. That's probably the case here. Yeah, it's a modified tetrahedral. So like I was showing you, I already erased it, but it's like a tetrahedral shape, but it's just more like kind of elongated. It probably should have been a little bit. Yeah, the carbon shouldn't have been so straight, actually. It would have been a little bit more of a bent structure. It probably would have looked a little bit more like this, actually. So yeah, it's like a modified, they call it a modified Vesper shape. So yeah, but it's still non-polar, and it's still going to be dispersion forces. So really, it would have looked more like that for propane. Yeah, the carbons wouldn't have been so much straight together because the electrons here want to repel each other. So yeah, it would have been a little bit more like that. Do I define the type or give you examples? You can just say the type. Yeah, because it's just asking what type of substances. So you don't have to give examples. You can just say substances that are non-polar with dispersion forces. You can just say that. Yeah, you won't see propane on the test, luckily. That one's kind of weird. It's not so straight. It's a little bit more tetrahedral, but also kind of bent. Sometimes these things have like more than one shape within them. Like I think there was one on a quiz that we had. I think it was a quiz, or it might have been a homework assignment. I can't remember, but it was like CH3OH. That one was like there was one that was kind of like that. I think it was maybe on a quiz or a homework assignment. CH3OH. It's tetrahedral here, but then it's like a bent structure up here. So sometimes they have like more than one structure within them. Yeah, let me know if you guys have any other questions or anything like that. If you want to see any other examples. Graham's law, yeah. So Graham's law, I think Ryan had a similar question a couple of days ago. And yeah, for Graham's law, you're probably not even going to be given like numerical givens, like no numbers in the question. It's just going to be, I'll just make one up right now. Right, so it might be something kind of like this, not these exact gases per se, but you won't have any numerical givens. It'll just be this gas and this gas are both diffusing through some opening in a container together. Which one's faster and by how much? So, we have the Graham's law equation. So this is CO2 and NO2. So the velocity of gas A over the velocity of gas B equals the square root of the molar mass of gas B over the molar mass of gas A. And that's the other thing I realized the other day too. Just try to be careful. These V's aren't volume, they're velocity, right? So the speed. I just want to make sure the gases A and gas B are like in diagonal directions to each other on this equation. They're not horizontally straight across. So I always just put the one that I know that's going to be faster on the top for the velocity ratio. That way I can just multiply both sides by V sub B and just algebraically do it quicker. You could do it the other way too. You could put the fast one down here. It's just maybe it's not as quick algebraically, but it's this. You'll get the same answer. So we just have to look at the molar mass to figure out which one's faster, right? So CO2. Let me put this on the side here. CO2 is one of those ones I always remember is just 44 grams per mole. Right, so CO2 is 44 grams per mole. NO2, don't remember exactly. O2 is 32. I always forget. I think nitrogen is 14. I think nitrogen is 14. Let me just put this in here just so I don't have to use a calculator. Molar mass of NO2. Yeah, so it's 46, just a little bit heavier. All right, so they're pretty close. CO2 is about 44. NO2 is about 46. So NO2 is slightly heavier. So since it's slightly heavier, it's going to be slightly slower. It's not going to be as fast. So that means CO2 is the faster one. So I'm just going to put CO2 on the top then. I just like to put the faster one on the top of the velocity ratio. Like I said, just make the algebra a little bit quicker. You can put it on the bottom. You'll get the same answer. I just like to make it quicker. So instead of A, I'm going to write CO2 down. CO2, CO2. Instead of B, I'm going to write NO2 down. CO2 is going to be quicker. It's slightly less massive. So I'm just get VCO2 by itself. Right, so multiply both sides by V of NO2. So VCO2 is the square root of the molar mass of NO2 over the molar mass of CO2 times the velocity of NO2. All right, so algebraically, like I said, it's just quicker to do it that way, just to do one step to get your variable by itself that you're trying to get by itself. So the molar mass of NO2 is going to go on the top of that radical. Molar mass of CO2 is on the bottom, right? So I'll do the next step over here. All right, so you're going to have this, and then 46 over 44, the 1/2 power. I don't have my calculator on me, so I'm just going to do this over here real quick. It's the 1/2 power. Yeah, so it's not that much faster. You get 1.022. So your answer for this would be the faster gas is carbon dioxide. So you can answer that question first just by looking at the molar mass. Whichever one's lighter is going to be faster. So the faster gas is carbon dioxide. And how much faster? It's 1.022 times faster. So it's not that much faster. It's only a little bit lighter than the other one. This one's only a little bit heavier. But yeah, so that'd basically be how you do it. It wouldn't be a question that has any numbers in the question at all. There's no numerical values. It's just this gas and that gas. So you would just have to look at the molar mass to figure out which one's faster and then just go from there. But yeah, the only numbers you really use here are the molar masses. Yeah, so let me know if you have any questions about that one. Oh yeah, no problem. I'm glad it was extremely helpful, and not just helpful. That's cool. Yeah, let me know if you have any questions there about any other examples you want to see. Oh yeah, no problem. And yeah, so tomorrow will be the test, but I mean, if you don't take it tomorrow, you can always take it later. Next week is spring break, technically, even though we're not in school. So I'm not going to post anything next week at all. I already started putting some stuff up for the week after spring break, but it's not visible yet. If you want to take a look at any of the notes or anything like that, you let me know and I can make it visible. I'm not sure, Ryan. Is that something you got in the mail for next year's classes, or? I'm not sure. I'd double check with your counselor, to be honest. But yeah, maybe double check with your counselor. I'm not sure, to be honest. I mean, we're expecting hopefully next year. Next year we'll physically be in class, hopefully. But yeah, for the rest of this year, we're just gonna be online. But yeah, I'm not sure what to do with that though. Maybe just ask your counselor and send them an email, and hopefully they'll be able to help you out. Yeah, because the school is pretty much empty. Only one assistant principal is there a day from like 8 to 12 for like 4 hours, and other than that, it's always empty. So I was gonna say maybe you can try mailing it, but I don't know. Yeah, it's kind of weird. It's strange not going back to school. I was kind of hoping we'd get to go back after May 5th, but it's yeah, I guess not. They just want to be safe, I suppose. Yeah, so let me know if you guys have any other questions you want to look at or anything else. So I won't post anything next week, but the next section is thermochemistry. So it's a lot of like heat, calculating heat, using mass and temperature changes and specific heat capacity as your values to multiply. So we know about mass, we know about temperature, but we don't know about specific heat yet. So we'll look at that next in a couple weeks. Not that I know of. I don't think so. Yeah, I don't think any like coworkers I know of have gotten it. Um, I know someone at my fiance's school got it, but luckily they stopped going to work like a couple weeks before they were told not to come back, so they should all be safe. So yeah, yeah, it's kind of bittersweet because yeah, it would have been nice to have gotten to go back to campus and worked with you guys in person. I feel like doing things online is just not as effective. It's yeah, it's harder to get points across and stuff. Yeah, well, I just found out. I don't know which program you're in, but excuse me. But I just found out that Citrus is still going to have their online summer school program. It's just going to be online instead of in person. So they're still going to have the summer school program at Citrus. It'll just be online. So I don't know if you're in a different one or not. I'm not sure about that one. Yeah, I usually work summer school at a different campus at Walnut High School, and I'm not sure if they're. I haven't heard from the guy in charge of it since like a couple months ago, so I don't know. Oh, Pomona College? Let me see. Hmm. On their page, it doesn't look like they've addressed the virus at all so far. Oh wait, no, they have. Oh yeah, it says here. Let me just see if I can send it to you. Yeah, it looks like. Yeah, there you go. There's a link that shows up on the top. It says learn more. It looks like they're going to be online. So I'm assuming that's with all the courses they offer, but I don't know. It looks like they're going to move to online though. So hopefully that's the same with all the summer school programs because that would really derail people's plans and stuff. And yeah, I just feel bad for my sister. She's a senior in high school. She doesn't go to Claremont. She goes to Lucerna over here in Whittier. Yeah, she's a senior. She's kind of like bummed that she's not going to see her friends until she like who knows when because they're moving off to other colleges far away and stuff, and it's kind of a bummer. Um, yeah, what are you taking to Pomona? So is it? It's not really like a specific course. It's just like other kind of stuff. Oh, okay. Oh yeah, it's only 30 participants each year. I think that's what it says here. I'm not sure. I'm sure it looks great on like things you can show to colleges though. Yeah, that's what I was gonna say. It probably looks really good. There's a picture of them taking a selfie on the homepage. They'll look really happy, like they're having a nice time. Unfortunately, I don't know if they'll be able to take selfies this summer. I guess a screenshot selfie. Yeah, it looks like 30 participants only. Yeah, let me know if you guys have any other questions or anything. Oh, so it's like 3 groups of 10 or 3 groups of 30? Oh, that's cool. So maybe like if you do it one year, are you guaranteed to be able to do it again the next year, or is it kind of like you already had your turn, so we're gonna let other people do it, sort of thing? Oh, okay, cool. So you're guaranteed to keep coming back then. That's nice. Yeah, it looks like it'll be online this year, but then hopefully, I'm assuming the years after it should be in person. There's like a crazy thing I read about today. Something happens, yeah, pretty close by us. An engineer near Los Angeles purposefully derailed his train. It went crazy, I guess. I guess no one got hurt, luckily, but he's some 44-year-old guy, and he was suspicious of the USNS Mercy, the ship there. They're using like as a hospital. He said he thinks they're not being used for what they say they're being used, and he was suspicious, and he wanted the train derailment to like wake people up or something. It's like some crazy stuff. So yeah, I guess some guy purposefully derailed his train today or yesterday. Really weird. I just hope the coronavirus doesn't shake up too many nutcases. Yeah, it's really crazy. I was shocked when I read it. I was like, what the heck? It's really weird. And luckily, I think it said no one was injured or killed, or at least killed, luckily, but it's like, come on. Like, oh, yeah, it happened on Tuesday afternoon, I guess. Okay. Yeah, he was 250 yards away from the Mercy. I guess he was trying to aim for it or something weird. Gosh. Yeah, that's pretty scary stuff. Yeah, so technically he's a terrorist then. They charged him for being a terrorist. Pretty crazy. I'd show you something interesting. Um, yeah, well, it's kind of like all the groups corresponds to numbers of carbons. Yeah, this is just for fun OChem stuff. You wouldn't have to know any of this stuff at all. All right, so that's meth, eth, prop, bute, pent, hex, hept. 8 is going to be oct. 9 is known. And 10 is dec. All right, so it's like for the number of carbons, those are all the prefixes. And so I'll just do alkanes, which means they just have single bonds. Alkenes have double bonds, and alkynes can have triple bonds. I'll just do alkanes just to keep it simple. But let me see. It's kind of like with other things we've seen before. Some of these can have multiple names. There's like more than one way to name them. Okay, I'll just do. So I'll draw it the long way, and then I'll draw it the shortcut way. Yeah, all the H's get kind of crammed together. It's kind of. All right, so it must be kind of hard to see this. So there's this big long alkane. So there's 5 carbons here, but then there's these 2 carbons that get branched off. So here, I'm just gonna draw it the shorter way. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, 5. So that's the shorter way to draw it, right? It's just the carbons as like corners. So the first step to these things is just finding the longest chain. So we want to double check, right? Because if we go straight across horizontally, 1, 2, 3, 4, 5 carbons. But let's double check if we start up here, because we could start up here. 1, 2, 3, 4, 5, 6. Ooh, I wasn't expecting that. Okay, so that's the longest chain then. I was at first thinking straight horizontally. So we have 1, 2, 3, 4, 5 horizontally. But if we start up here, 1, 2, 3, 4, 5, 6, the longest chain here is 6 carbons. So it's 1, 2, 3, 4, 5, 6. So that's the longest chain, the 6 carbons in a row. And I started with number 1 up here instead of there. And that's important. There's a reason why I did that. I put number 1 up here, not down there, because this is closest to the branch. Because over here, there's a carbon by itself on this little branch. It's not part of the main backbone. Like this big carbon chain is like the backbone of the molecule. And there's a little branched carbon over there. Right, so I start my numbering closest to the nearest branch. So this is 2 carbons away, and this one's 3 carbons away, so I'm gonna start up here. So 1, 2, 3, 4, 5, 6, like that. So the first thing you wanna do is you name where the branch is. So on the 3rd carbon, coming off of the 3rd carbon, I have a carbon right here. How many carbons is this? This is 1 carbon. So 1 means meth. Right, so I'm going to call this 3-methyl. So yeah, all the rules get really crazy and confusing. So I put 3 down because that's the carbon in the backbone chain that the branch is on. The branch is on the 3rd carbon. So 3-methyl. I put meth there because it's 1 carbon. Right, there's only 1 carbon here. But for branches, you end it with YL, like ill, so 3-methyl. And then we're almost done. This is just the name of the big backbone. So the big backbone is 6 carbons, 1, 2, 3, 4, 5, 6. So 6 is hex. So it's going to be hexane. So yeah, that's the name of that thing. So yeah, we're probably not going to have time this year, unfortunately. But like I said, I like to do at the end of the year some of this like nomenclature stuff for alkanes or alkenes and alkynes, usually just alkanes. Alkenes and alkynes can get kind of more complicated because there's a double bond somewhere or a triple bond somewhere, and then you have to number off what carbon those are at too, and so it gets kind of crazy. But yeah, so that's that one. It's pretty cool ones. Let me see if I can find another one, just because they're kind of fun. I'll do another alkane. I won't draw it the long way because that's just all the H's get too much in the way. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this one's pretty complicated. So we first just want to see where the longest chain is. So if I go straight horizontally, that's 1. Oh, you can't see that. We go straight horizontally. It's 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. That's 8 carbons. But let's try another path. Let's try this one. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, that's also 8 carbons. So sometimes you get this weird case where you can choose one path and maybe it's a certain number, like 8 carbons, and then a different path and you'll get the same number, 8 carbons. It'll work either way. Right, it'll work either way, and I'll show you why. So I'm just going to go horizontally across 1, 2, 3, 4, 5, 6, 7, 8. So I'll start over here with number 1 because that's closer to this branch. I don't want to put number 1 over here because that's further away from the branch. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, like that. And so notice on the 4th carbon, you get a branch of 3 carbons here, because again, each corner is a carbon, 1, 2, 3. So off of the 4th carbon, you get a branch of 3. So let's see if I tried it the other way. If I tried it the other way, 1, 2, 3. I'm going to get the same name if I tried it this way. 1, 2, 3, 4, 5, 6, 7, 8. And again, off of the 4th carbon, I get a branch of 3. 1, 2, 3. So it always kind of works out that way. So we could have chosen the path either way. I'll just stick to horizontal. So 1, 2, 3, 4, 5, 6, 7, 8. But again, the 4th carbon has a branch of 3. That's a a propyl group. So you want to first designate where that's at. So 4-propyl, kind of like that, 4-propyl. And then just end it with the name of the whole entire thing. So there's 8, so that would be 4-propyl octane. They can get more confusing if you have more than one branch. Like we might have had, like in this case, we have a propyl group on the 4th carbon. Let's say we have more than one though. Let's see if we have a different branch. Let's say on the 3rd carbon we have a methyl group. Right, so I just changed it. So on the 3rd carbon we have a methyl group, 1 carbon here. On the 4th carbon we have a propyl group, 3 carbons here. So we have to name both of them. And so if you're wondering which one do we name first, it's basically alphabetical order. So methyl is on the 3rd one, so it's an M. Propyl is on the 4th one, that's P. So we're going to name the methyl one first just because it's alphabetical order. That's pretty much it. So this one would be 3-methyl 4-propyl octane. And you know what? Let me double check. It's not a big deal, but I think I'm adding an extra dash here that I don't need. Yeah, I don't need that last dash. I can just put octane right afterwards. I think before I was putting a dash there, but I can just combine it with that last group. So 3-methyl 4-propyl octane. So 3-methyl, because on the 3rd carbon I have 1 carbon here, a methyl branch. And on the 4th carbon I have a propyl branch here. There's 3 carbons there. And again, I put this one first, not because it was first in the chain, but just because of alphabetical order, because M's before P. So that's pretty much it. So that one's kind of interesting. I just like doing these because they're always kind of fun, and it's always just kind of satisfying seeing it look all nice and official like that when you're done. During the summer school program I usually do at Walnut High School, we spend a lot of time on these things because it's like an accelerated like honors chemistry program, and they have to like know all the stuff because they're going into AP Chem like during the school year right after the summer. And sometimes instead of getting a drawing and doing the name, sometimes you're given a name and you have to draw it out, so it can go both ways. So yeah, sometimes it gets kind of weird. Let me see if I can find an example. Yeah, there's other prefixes too. So for example, if it's like 15 carbons, because we only stick to the first 10. But 5 carbons is pent. So from 10, it'd be pentadecane for 15. I don't know if there's really a shortcut. Not that I remember. Yeah, not really like not much of a shortcut. Let me see if I can find a crazy one here. Just waiting for it to load. It's taking kind of forever. Okay, I'll just do this one instead. Okay, open image, a new tab. Some of these ones are kind of long. I don't know if it's gonna copy in here. I don't think it is. Well, I'll just send you the link to the page. Yeah. On the 3rd carbon, it's like 3,3 because there's 2 of them, and then you have to put dimethyl because there's 2 methyl groups, and so it gets kind of weird. You said mitotoxin. Yeah, they might have shortcuts. Some of these ones that are extremely long. Yeah, and that one is kind of complicated because it's made of a lot of these benzene rings. It's a lot of these cyclocarbons. So yeah, something like that. Yeah, that's a pretty long one. So they're gonna definitely have like a shorter name for some of them. Oh, it looks like it was used as like mice poison. Yeah, because there's other weird cases of naming things where it's like you have these cyclical things. I'm not the best at drawing them. It's supposed to be like a hexagon, right? Like 6 carbons. And we call them benzene rings, but there's always like double bonds separated. So it's like there's a double bond between those 2 carbons, a double bond between those two, and a double bond between those two. Um, and then sometimes you have to name those branches too. So like 1, 2, 3, 4, 5, 6, and you would just call this. Although you don't really have to name them actually. So if I had something like this, we call this like little hexagon structure a benzene ring, and we have an ethyl group here. There's 2 carbons, so it's an ethyl group. So this would just be ethyl benzene. Ethyl benzene. And then there's other ones that don't have double bonds, but maybe like kind of like this, for example. It doesn't have to be a hexagon. It could be like a pentagon in this case. I'm just not that great at drawing these shapes. So in this case, propyl group. So this would be propyl cyclopentane. So you call it propyl cyclopentane. Cyclo because it's like circular. It's not circular, but it's they're in a loop, a closed path. And cyclopentane because it's 5 carbons. It's like a pentagon shape. Some nitrogens and oxygens in it. It looks like. No, it has sodium, sulfur, and oxygen. So if there was like a longer, more official name, it probably involves those functional groups that have like the oxygen with it. Yeah, it gets kind of crazy. Yeah, let me know if you guys have any other questions or anything. I might have to head off in a few minutes. Yeah, so if we have time, it'd be fun to do some of that OChem stuff, but I mean, it'd be extremely hard to teach like online. I guess I can I'm sure I could do it, but it's easier to kind of see you guys doing it, and then I guess it's just the way of any of these concepts though. But yeah, that stuff is definitely fun. Yeah, I'll probably head off in a couple minutes. Just let me know if you guys have any other questions about the study guide or anything like that. That could probably work. Um, yeah, I'm sure we could. I'd have to like kind of like with live streams, I'd have to let everyone know like what time and what day we would do it in case they'd be interested in trying it out for review. Um, yeah, we could theoretically do that. I'll see if I can try doing something like that for the next unit then. Yeah, we can try something like that, like a long distance Kahoot. I'll try that next time. I didn't think about that, but that'd be a cool idea. Do you guys like Kahoot more or Gimkit? I feel like Gimkit seems like it's more fun because you can like it's more competitive. You can like punish people and give yourself more money and stuff. I just feel like that's just my opinion, but yeah, I'll probably head off in a couple minutes or so. Just let me know if you have any questions. Yeah, I think Gimkit's probably a little bit more fun. It's more competitive. Yeah, if you guys but yeah, check out the solutions to the study guide and stuff. They're online on Canvas, so the solutions are on there, and what's it called? The solutions to some of the homework problems are on there too. If you guys need any help. Yeah, it's tomorrow, but I mean, if you don't take it tomorrow, you can always take it later. The window's pretty open. Next week is spring break, so I'm not gonna like post anything next week at all. I'll just be pretty silent. So, but yeah, you'll still have time to take it like over the weekend or something if you need to. But yeah, the solutions of the study guide, they're online and stuff like that. So it's not going to be more difficult than the study guide. It'll be like as difficult or less difficult than that. So hopefully it's not too bad. Yeah, it'll be tomorrow, but it's not timed or anything either. Anyways, I'll probably head off now. Just a last call if you have any last minute questions or anything like that. Yeah, I hope you guys have a nice rest of your day and stay safe. Yeah, the test will be tomorrow, but like I said, if you need some more time, you can always take it in the next few days or something. It's open for at least a week. But yeah, have a good one, guys. Take it easy. Nice interacting with you all. Have a good one.